talking about circuits. And there are a ton of questions on the AP exam with circuits, especially in the multiple choice, because there's a lot of like little short, quick kinds of questions they can ask. But the bottom line on circuits is, well, we're going to slowly add components to it, is you have a battery, you have a wire, you have a resistor, and it makes a loop, something like that. That's the simplest possible circuit. And so how do you think about circuits? There's a few things. First of all, let's talk about symbology. The battery is drawn like this, with the big side on the positive side and the small side on the negative side. And it's assumed that if you have a battery like this, it's assumed that the current leaves this way from the positive side. Okay? It's the direction of positive current, but really it's electrons that are moving the other way. So an electron moving to the left is equivalent to a proton moving to the right. But so really, we think of this as protons going this way, but in truth, it's really electrons going that way. But that's just a little aside. So we assume that it's this way. If you have a circuit where there's two batteries in it, and you have something like this, how do you decide which way the current's going? If you say it's going this way, then you're going to run into trouble with that one. And if you say it's going this way, then you're going to run into trouble with that one. So you just pick a direction, and then there'll be some minus signs that show up later on. So if you're not sure which way the current's going, pick a direction and live with it. Okay, what game do you play with circuits? Well, the idea is to, ultimately you're interested in knowing about things like the voltage at any point, the current at any point, the resistance, I suppose, could become important. But it's usually, in charge, that's another thing. So usually we're interested in knowing how much voltage there is, how much potential difference, what the current is at a certain point, or sometimes how much charge there is on a capacitor. So those are the things you're kind of interested in. So there are some rules. So we're going to be generating equations so that we can solve them and figure out these things. And to generate an equation, one key idea, there's only like maybe two super key ideas, but one super key idea is that if you pick some random spot right there, let's say, we can call that point A, I guess. And if we start at point A and we go completely around the circuit and get back to point A, we can be sure that the change in potential difference will be zero. So you might lose a little bit of potential difference as you go across the resistor, and then you get it back as you go through this battery, and you get back to the original spot. And this is called the loop rule. And the loop rule says that the total change, I guess it's a change, in the potential difference is zero for a full loop, if you go all the way around. So we're going to choose this as our current direction, and we can say that anytime you cross a resistor, you're going to lose oomph. And voltage is like oomph. And so there's going to be a drop in the push, because the electrons are getting pushed pretty hard by the battery. After they go through this skinny little spot like this, they're getting pushed less. Imagine traffic. And you start your car, and then you run into a resistance area where the traffic is thick, or the road is narrow or bumpy or something like that. When cars come out on the other side, they're going to be going slower. They're going to lose some of their, because they had to slow down and all of that, so they're going to lose it. So anytime you cross a resistor, you're in the direction that the current is flowing, you're going to lose some potential difference. And this comes directly from our old expression V equals IR from previous chapters. We've seen that before, right? Right. Okay. Anytime you pass by a battery, you're going to gain some voltage, but it's given this funny symbol E, which is the symbol that stands for, what is E for? E stands for the electromotive force. I'll write it down. Electromotive And sometimes it's just abbreviated EMF. But that's an acronym. Although if you play Words with Friends, they will allow that word even though it's really an acronym. Oomph. But it's kind of an interesting word because that's kind of what the battery does, is it gives it some oomph of the charge as they're going along. So it's kind of not a terrible word. So anytime you pass by, you gain a plus E, and we'll talk about that a little bit more in a second. And so the loop rule would say that 0 is going to equal the minus IR plus the EMF that we gain at that spot right there. Okay. And so we can figure out so maybe they tell us the voltage of the battery. And actually, maybe here's a good time to mention that we have two kinds of batteries. We have an ideal battery and a real battery. And in an ideal battery, the EMF is equal to the voltage of the battery. You buy a 1.5 volt battery, you get 1.5 volts of oomph. A real battery, though, has, because of heat that's generated inside of it, has a little bit of internal resistance. And so in a real battery, the voltage that you get is equal to the oomph, the EMF, the electromotive force, minus a little bit of internal resistance, and we'll just say minus IR. Let's let that little r represent the internal resistance of the battery. Okay? And normally they will tell you, a problem will say it's an ideal battery or a real battery. If it's a real battery, there's going to be perhaps some calculation of the internal resistance. Make sure I have that just right. Yeah, does it match what we saw? Yeah, good. Okay, let's take a look at a more complicated circuit. Let's say we've got two batteries, and let's make them screwy so they're talking at each other. Let's go like this. We'll just make it slightly more difficult than the one before. And let's say these are ideal batteries, and let's say this has an EMF of, 7 volts, and let's say this has an EMF of 4 volts. Let's say this has a resistance of, 50 ohms. Okay, and let's say here we're interested in finding out how much current flows through the 50 ohm resistor. So we're going to find I. Okay. So first thing we're going to do is choose a direction for our, these are ideal batteries, we're going to choose a direction for our current. Here it looks like clockwise makes a lot of sense because I think the 7 is going to dominate the 4. So that will be our chosen direction for the current. And now we're going to pick any old spot that we want on here. Let's pick this spot right here. We're just going to go through and start with, we're going to do the loop rule. We're going to go all the way around, and every time we pass by an element, there'll be either a gain or a loss of voltage. So, as we go this way, will it be a gain or a loss as we cross this way? This battery is pushing the currents coming off the big thing. So here we're choosing a current that's going against the battery. So we are losing voltage. This one pushes it this way. This one's going to kind of go against it. So this is going to be minus I times this voltage, 4 volts. Now the current goes this way. The current is going in the direction of the resistor. We're going to lose current as we go through. We're going to lose potential difference as we go through there. And that's IR every time we pass through a resistor, minus IR. I made a mistake. Get back to that in a sec. I don't need an I there. It's just the EMF like that.
That's what I was, okay.
No I on that term. So it's a minus 4 minus an IR where the R is 50. And then going through this battery, it's a plus 7. And that brings us back to where we started, and now it equals 0. So it's going through each element, right? So that means, what do we have here? So that's, move the 7 to the other side, move the 4 to the other side, we got -3. Multiply both sides by -1, we have 3 equals I times 50. And so I equals 3/50ths, or 0.015 amps.
Yes.
Okay, let's take a look at a slightly more complicated circuit. We've got a couple minutes to do one more circuit here. Later on in our next lecture, we're going to introduce capacitors, but right now we're only looking at batteries with resistors. Let's pick a single battery. But we're going to go like this. Okay.
So,
And let's give these resistance numbers. Let's call this 2, 1, and 1. And let's say that those are ohms. And let's say this has a voltage of, let's say, 6 volts. And let's say we're trying to find the current at point A and the current at point B. Okay. So I see more than one loop.
yes.
I see 3 loops. Do you guys see 3 loops? The big one
Yes.
and the 2 little ones. That means you have 3 equations. So you can make as many equations as you have loops. Let's choose this as our direction of the current, I. At this point right here, that I is going to split. Some of the I is going to go this way, and some of the I is going to go this way. We can call this I1, we can call that I2. Here's your second rule. So we have the loop rule, and now we also have the junction rule. And anytime you come to a junction, whatever current you have going in is going to split. So that, in this case, our junction rule, JR, is going to be that I equals I1 plus I2. Make sense? That I is going to split up into 2. Just like water flowing, some's going to go in the left stream, some's going to go in the right stream. Now we've got 3 loop rules. Loop rule 1, this is my own symbology, I've never seen this before. Loop rule 1, loop rule 2, loop rule 3. So let's start with this first inner loop right here. They're all going to have a 0 equals 0 equals 0 equals, because it's always 0 all the way around. I'll start right here. So I'm going to lose I times R, I times 2. I'm going to lose I1 times I1 times just a 1 ohm resistor right there, right? It might have been better if I worked all in variables.
Yeah.
Shall we do it?
Yeah.
Okay. We'll just call this R2, R1, and R1. Because those are going to be the same size. So this is R2, R1. And we got to complete the loop now. We have no voltage loss through just metal. Not until we get to an element do we have anything. Oh, it's a gain of +6. We're going to assume it's an ideal battery with no internal resistance. Okay. Equation 1. Equation 1, equation 2. Let's do, this is our next loop. Pick any starting spot we like. Any starting spot we like. I'm going to drop some resistance across R1, so it's going to be minus I2R1, minus I2R1. And I'm going to keep going around. Nothing, 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 nothing. Oh, this is my first time that I have the, I'm not going with the current. The current's going this way, but our loop is going this way, right? So instead of this being a minus as it goes through here, as it comes back this way, it's going to be a plus if we're going against the current. And it kind of has to be if we're going to have something add up to 0, one negative term and then another positive term here. So we're going to have a plus because we're going now not in the real direction of the current, plus I1R1. Okay? And let's see if that's okay. And then my last loop could be the whole big one going all the way around. So let's see. So at this first one here, I'll start at this point again here. So I'll have a minus I R2 going this way in the big loop, minus I2 R1. Going, continuing on, metal, 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 metal. Whoa, what I do I have right here?
I again.
It's the full I again, right? Because these two are going to split and come back together. So it's back to the full I, and we're still, oh, and now we got a plus 6. And we've made it back. So we have 4 equations, and we have the bell. That's a solvable system of equations, and then here we'd be solving for I, I1, and I2. We have 3 unknowns, but we have 4 equations. So technically it can be solved. Takes a little bit of work. Just algebra from there. That's a good place to stop. We'll deal with capacitors in the next lecture.